Good morning, Daniel.
Good morning, Pasha. Hey, Ying, are you around right now?
Yeah, Daniel, hello.
Oh, hey, how you doing? I just had a
Can you hear
couple
me?
quick things. Yeah, I can hear you just fine, actually. Just had a few quick things for you. I noticed that you uploaded two slide
Slides,
decks,
yeah.
and one of them had the LPC graphics and one didn't. I just was not sure which one you wanted to use.
I will use the one with LPC graphics.
Okie doke. All right. And then you also had an animated GIF file that BBB doesn't seem to allow me to upload. So I'm not sure if you wanted to try to convert that to a different format, or if you were relying on that.
Okay. No, I do not rely on that. Yeah, it can be kept there for people who have interest.
Oh, okay. Awesome. Cool.
It appears my network status isn't good, so to guarantee the quality of audio, I may present without camera. Is it okay?
Oh, that's just fine. Yeah, that's perfectly fine.
Thank you.
everything all set in this room?
We do seem to be okay in here. So far, so good.
Great. All the slides been uploaded?
We're waiting for one more talk, but I've emailed the speaker, and he won't be going for a few more hours.
But by the way, even during a talk, I've done this before, you could kind of steal the presentation and then upload it and then give them back to presentation. I've done that to some people before in the past.
I
So,
see.
Uh, yeah. Also, did you make sure that you marked all the presentations to be downloaded?
I did, yes. One question about the time left slides. When
Yes.
I use those, I guess I'm going to get rid of the slides of the speaker, right?
Yeah.
Okay. So
So what you do is, like when you click the plus, you should see all the slides that are available. And then just click once the person's done. Wait, for the time left, like 5 minutes and all that.
Yeah.
You could do that. Did you not get one of the? I guess. Wait, you probably didn't get the speaker's gifts, or?
I do have the actual cards as well. So I guess a better way would just be to flash them up on my camera. So
That's what I do. It's less disruptive to the talk.
Okay, yeah. I think I'd seen it done a different way, which is why I'm asking. But yeah, that sounds a lot better. So I'll do. I will use the cards themselves, the physical items.
Yeah, I've seen both ways, and I thought the way of taking over the presentation and putting up the 5-minute slide was more disruptive, especially when the person said, "Can I have my slides back because I want to show something?" So that wastes time.
I was one of those people. Yeah.
Okay. Yeah. So
for sure.
Yeah. So the card, if you have the cards available, those are much better. That's what I did in my MC yesterday.
Okay. Cool stuff.
Okay.
Thanks.
Anything else? By the way, I usually tell people another nice thing to do is, since you can't have shared notes and chat up at the same time, do you have the link for your chat list doing it through the website?
Well, let's see. I've got the website up. I don't have the link.
Let me see. This is.
But I suppose if I just copy the URL from the browser, that should work. Let me see. I can paste that in the shared chat up at the top.
Remind me which micro conference I'm in. I just jumped on.
Performance and scalability.
Performance and scalability. I'll put it in the link.
In the shared notes, I've got the link. I'm not sure.
If you got the share. See, I'll check the shared notes. Yes, that's it. So for those that are taking notes and also want to contribute to the chat, what I did was I opened up another browser window and go to that link. So then you just switch between browser windows. So you don't have to, because to switch between chat and shared notes, it's time consuming. You want to look at one or the other. So I found it much more efficient to have a separate window with the chat up and have the notes here to take notes.
Okay. All right. We can mention that to everybody when we're getting started.
Yep. And just the people that will be taking notes. If there's anyone that isn't interested in the notes, they could stay right on the chat. That's so.
Okay. All right.
Okay. Great. Good luck. And I'm going to be bouncing around the other rooms now.
All right. Thanks, Steve.
Hey Daniel, so that link you pasted in the shared notes, right?
Yeah.
Is it the chat?
Yeah.
Interesting.
And I'll write a little note about.
Yeah.
Why it's
Yeah, my password doesn't work for that. Are you able to log in using that link?
Yeah, there's a little bit of a gotcha there. So you have to replace the @ sign in your email with a dot, which they do show in the email that James sent. and
Oh, okay.
but it's easy to miss. Yeah.
I see. Right. I suggest you add that information about you username here as well. That use that instead of add.
All right. Good idea.
Hi, everyone. I'll give it one more minute before we kick it off. Can everybody hear me okay?
Yes. We can hear.
All right. Thanks, Pavel.
That's fine, Dave.
All right, it's on the hour. Let's go ahead and start this. On behalf of Daniel, Pavel, myself, welcome to the Performance Scalability track. We would like to thank our sponsors, Diamond sponsors Facebook, Platinum sponsors IBM, Gold sponsors ARM and Microsoft, Silver sponsors AWS, Amazon, Netflix, and Red Hat, and the speaker gift from Collabora. T-shirt sponsor is VMware, Conference Services, the Linux Foundation, and I'm sure you can read all that as to how to be a decent human being. Yeah, the idea of this is to have debate, try to upstream things that have not yet been upstreamed, and depending on the speaker, he might or she might let you interrupt at any moment, or leave questions for later. But the idea of this is to generate debate. So with that, I'm going to kick it off to Yang with the first presentation.
Jack, there we go. Yeah, now I can control it.
There, I gave you presenting permissions, so you should be able to take it from here.
Oh, yeah. Now I can operate on it. Sorry, it appeared it had not displayed for me.
So you can't see the slides, Yang?
It's oh yeah, I can see it now. Yeah.
Okay, good.
Sorry,
good.
yeah, sorry.
We can hear you
The
okay.
network status isn't very well.
Uh,
Okay, great.
Okay, cool. I will let you get
Okay,
started then.
Thank you. Hello everyone. Sorry because my network connection status isn't very well. I will present without camera. So thanks a lot for join our discussion about optimizing page placement in tiered memory system. So today we will talk about firstly some background about memory tiering, then about demote the code pages from DRAM to PMEM, where something like migrating in lieu of discard, and promote the hot PMEM pages to DRAM with new balancing, and the to-dos, evaluation, and some alternative implementation.
I'm not sure if the internet dropped.
So I just see that Ying has dropped offline in my
Okay.
networking information.
Is
Let's see.
yeah, is Dave Hansen?
He
Yeah.
has popped back in,
Dave.
but he doesn't have
Oh,
very many bars.
okay. Let me know if you want me if it happens again to give you the presenter rights.
Sure. I guess I can fill a little bit of time while Ying's coming back on. So yeah, in general, we have these new pieces of hardware with different kinds of memory. And so we've been up to this point using plain old NUMA APIs to let people move memory around between these different types, because some of them are faster and some of them are slower than we've traditionally had. So Ying's agenda here is to talk about some of the things we're doing inside of the kernel to make these things better. Right now, we've been relying on user space, but user space doesn't, for instance, swap pages historically. So we figured we'd add some things to the kernel that would let you let your applications kind of continue to be unaware of these tiering setups and still get some of the benefits of them. So a couple different approaches here that Ying is going to go through, hopefully. Is Ying back yet? Otherwise, if you give me presenting rights, I'm happy to go through, especially the overview and the discard portions. So.
So I see that he's in the room, but his bars are pretty weak. So I'm going to go ahead and hand it over to you, Dave, if that's okay, unless we hear from Ying. All right, so I'm going to make you presenter right now.
Okay.
You should be able to control the slides at this point. There you go.
Yep. I can control them. Great, thanks. Okay, so historically what happened is that all RAM on our systems were DRAM. Everything was pretty much the same. We had NUMA systems, and so the RAM may have had different locations, but all RAM was DRAM, all of it was the same, nothing was different. And recently we started to get some changes to this. So we've got persistent memory, which is a new member in the hierarchy. It's great, it's cheap, and there's lots of it in systems, but it's relatively slow, especially on writes. There's also high bandwidth memory. We've had a couple different versions of this over the years, and this exists on other platforms, other than x86. But essentially, it's closer to the CPU, but it's really expensive, and there isn't very much of it on the systems. And then the newest emergent thing that's happening is CXL. This is essentially fast PCI devices, but the cool thing about these is now cache coherent. And so you can throw some persistent memory on one of these devices or throw some DRAM on them, and you can expand system memory just with a plug-in card. It'll look externally like PCI, but you can plug it into a system and use it like RAM. So pretty neat stuff. So essentially what is a new member in the hierarchy between the CPU cache and storage. Traditionally DRAM was the only thing in here, but now we have things above DRAM and below. This picture just shows PMEM, but essentially we have two new we have things that are both faster and slower than DRAM that are showing up. So this is also an example of what we do right now in the hardware. So on the left side here, we have
hello, Dave. Sorry.
Hey, Ying. If your audio is back, feel free to take back over.
Thanks, Dave, for help to adjust. Thanks. So yeah, I will continue. Sorry for my network connection status isn't stable. So yeah, we have memory mode that it is fairly transparent to OS. It has good enough performance for some use case. The hardware, in fact, the memory controller will control the page placement, so there's no page placement control from OS or application. So it has lowest complexity, lowest barrier to adoption. You will lose the DRAM capacity, and the PMEM can only be used at volatile memory. And we also have APP direct mode, which is fairly non-transparent. The application will control the placement. So because the application may know better about which page is hot, so it may have best performance. and in the same time, it has highest complexity, the highest barrier to adoption. The DRAM capacity is maintained. The PMEM can be used as persistent memory. What we propose in this slide, in this talk, is something in the middle, the memory tier mode, where the OS will choose the default placement, so the placement can be transparent to application, but the system admin or application can also override the default placement. So it can replace APP direct mode except persistent. It has low barrier to adoption. The DRAM capacity is maintained, and the PMEM can be only used as volatile memory. So for the optimizing target, we want to optimize the page placement automatically. That put all hot pages in DRAM and cold pages in PMEM. It should respond quickly enough to access pattern changing. It needs to balance between the overhead and accuracy. It should be manageable. For example, we may partition DRAM among workloads. It should be flexible, so applications can override the default page placement. Yeah, this is about represent the PMEM. So for example, for a system with 2 sockets, we will put the CPU and DRAM in one NUMA node, just as before. But for the PMEM in the same socket, we will represent as a separate NUMA node. In this way, we can use the existing NUMA API to manage PMEM, and we can take advantage of some existing NUMA mechanism, for example, NUMA balancing, or the area or the per NUMA node area list, which we will use in later.
So Ying one he's still here.
Oh, sorry, I just dropped that. Okay.
Yeah. So Ying, one question here. So with
Okay.
the CXL, how this figure will change?
So yeah, we will put PMEM in move. Okay.
Ying, I didn't hear the answer. You dropped out for a second in the middle of a sentence.
Sorry, the audio quality isn't good for me to get your idea. So maybe we can go back to here later. Sorry about that. I think it's because of my network status. So about demote the code DRAM pages to PMEM. Yeah, we leverage the page reclaiming when there is mem pressure in DRAM node. The page reclaiming will be started, and it will identify code pages in DRAM and try to, instead of discard these code pages, we will try to migrate these pages from DRAM to PMEM. The RU algorithm used by page reclaiming is good at identifying code pages. So so far in test, this solution works quite well. And even for the further potential page reclaiming algorithm improvement, for example, the multi-generational RU algorithm, we can take advantage of it.
Oh,
The basic part of the demotion has just been merged by upstream kernel version 5.15.
Hey, Ying, could we just go back to the previous slide? So the whole migration loop discard is kind of interesting. Because...
Oh, sorry, Matthew. I think because of my network status, I cannot hear your question clearly enough. So
perhaps I should
sorry
type
about
that.
If you want to go and ask Matthew, go ahead, and I'll answer back if I can as well.
Okay, go back to previous list.
Matthew, you can go ahead and ask the question.
Okay, so I'm worrying that we're actually going to be slowing down some workloads by moving pages around the active list and then copying them over to PMEM and then copying them to storage again. I kind of feel like we might be better to use PMEM as a victim cache. So when we're going to get rid of a page, we write it to swap and to PMEM, and then we retrieve it from PMEM if it's still there when it's going to become active again.
Matthew, I believe that's how it works exactly. So the place we plugged into the VM here is right at the point when we would have decided that there are no more references to the page and thrown it away. So actually, swap space has been allocated, and the writes should have been started by the time we go do this. So it's clean and ready to be discarded. And so just to the point that we would have thrown the page away that we copy it. So it's actually in swap for anonymous memory.
Okay. So
It has some downsides, but it is how it works right now.
No, I mean, I obviously I think that's a legitimate way to do it because that was what I was just suggesting. So when we come to reactivate that page, so it's referenced again, do we leave the data in PMEM or do we migrate it back to DRAM?
I think what was merged so far doesn't have the promotion part.
Yeah, Matthew, right now it will stay in PMM. It's lazy about it, so it's stuck. And we know that's a problem, and that's what Ying's going to talk about in terms of what we're proposing to rectify the problem of it getting stuck in PMM.
Okay.
The only way right now it would get promoted back to DRAM is if it went down into swap, and then the swap cache page got evicted out of PMM, and then it got faulted back in from swap. It would tend to go back to DRAM. That's the only way it can happen now. That's not great, and that's what Ying's going to talk about fixing.
Cool.
I kind of Matthew, you said that it will slow down to do it proactively, but so what can happen is that we can have once the RAM is full and we like have a sudden spike in allocation, we would have to start moving lots of pages to the PMEM, which will also slow down, right? So PMEM is much larger, and I think it makes sense to proactively move rarely accessed pages to PMEM instead of waiting for like memory pressure and for swapping to start.
That's a good question. I mean, but it's kind of orthogonal to this because right now we're pretty much saying we're going to take what the VM does and we're going to do this little tweak to its behavior. What you're talking about is something. I mean, we've talked about proactive reclaim and user control of the reclaim process, like with the multi-gen LRU or the other things people have done. I look at those as being really orthogonal. There's lots of other things we could do to the VM in general. We can use them with these memory tiering systems, but I think those are kind of orthogonal problems.
So Dave, one question I have is more so currently, since it depends on the reclaim, it's only looking at the LRU pages. I'm wondering, is there a plan or to look at the either unevictable LRU pages or non-LRU pages like HTLB and stuff?
People have asked about it. I didn't have any immediate plans to go look at it, but people have asked about it. I've told them for each of BFS, they're switch to THP if you care. So that answer has worked so far. So no plans, but we could be talked into it.
Matthew, could you then please repeat your initial question? I might have misunderstood your first question regarding this diagram right here.
So this diagram confused me because what this diagram is saying to me is that when the page becomes inactive, we migrate it to PMEM, and then once the page becomes inactive on PMEM, we migrate it to storage, and that isn't what's happening at all. So this slide just confused me. That's all.
I see. I got it. Okay.
Yeah, that's a good point, Matthew. It actually kind of hits storage first. It probably hits storage first before it goes to PMEM. So you're right. It's kind of from a very high level how we think of it, but it isn't how it happens in practice for sure. Ying, are you back? You're probably welcome to keep going.
But Dave, but for a long page,
I'm
but
back.
for a long page, we do actually go to PMAN first, right? And at least the patch set will go to PMAN first, then swap to disk. Is that correct?
Well, I hope I'm not forgetting what actually got merged. But if I remember correctly, the point when it decides to do the migration is at the point when the last reference to the page would have gone away. So instead of having that last reference go away and us actually freeing the page, we do the migrate pages at that point. So at that point, the page is in the swap cache, has been written to disk, is clean, and that's when we demote it, if I remember correctly. Because people have also complained that it does require swap activity for the demotion to occur. So now it's possible it changed and I've forgotten about it. I'm remembering an old version, but that's my recollection of how it works.
Okay, Dave, I don't think you remember correctly. I think the anonymous page just got migrated to PMEM node. No matter it doesn't go to swap cache at all.
Okay, totally possible. You can probably keep going.
Okay. Sorry. I cannot hear all your words clearly or in time. Sorry about that. So for the to-dos, now we will just have the basic part of the migrating your discard merged by the latest upstream 5.15. We still have some to-dos for demotion. Firstly, we cannot discard the evictable pages, but we may migrate them to PMEM. Yes, and we have some reclaimable but unmovable pages. For example, the inode, the entry cache. Because we can migrate the, for example, a non page of file caches, it appears that we can think about how to deal with the reclaimable pages in this situation, maybe lower the scan priority or something like that. And we lose the resource feedback because we migrate the pages instead of swap them. We may think about how to retain the resource feedback. Yeah, we cannot discard huge TRVFS pages too, but we may consider is it possible to migrate them. And some new policy information isn't available during page demotion, page reclaiming, but we may think about how to comply the new policy as much as possible during the demotion. So about the promotion, we do that with NIMA balancing. For some background, NIMA balancing is used to reduce the cross-socket memory access. It will scan the page tables of all make page inaccessible. So later when a page is accessed, the NIMA hint page fault will occur. And if the page is identified as remote and it is not shared by multiple sockets, it will be migrated to the local node. Because we represent the PMEM in a separate node, so all PMEM accesses will be considered remote access. So when we access a PMEM page, we will try to promote it to DRAM. So the original NIMA balancing works for the PMEM naturally, but there are still some problem. Firstly, what if the DRAM is full? And in this way, we promote the most recently accessed pages, but whether these pages are hot. So firstly, about the DRAM is full problem. When the free pages in a DRAM zone is higher than the high watermark, we will promote the hot PMEM pages to this DRAM zone or DRAM node. But if the free pages of the DRAM zone is lower than the high watermark, we will wake up the key swap D of DRAM node. And we change the key swap D so that in this situation, the key swap D of DRAM node will reclaimed so that the free pages of the DRAM zone will be higher than not only the high watermark but also the promote watermark. The promote watermark is higher than the high watermark. So in this way, we demote and promote pages between the high watermark and the promote watermark. So if there are heavy memory pressure in DRAM node, we will stop promotion so that we can leave the free pages between lower than high watermark for the high memory pressure. Yeah. So the promotion, so this way the promotion will not make the main pressure too high, too heavy. So I think this kind of balance between the DRAM utilization and the main pressure. So if you want more memory, free memory, you can use the you can raise the high watermark or something like that.
Ying, I have a question. What's the cost of this for the overhead for on machines that don't really suffer from memory pressure or aren't really doing swapping at all? Is there a performance cost for this if you're not using it?
Yes.
Since you're periodically scanning.
Yeah. Because sometimes the promotion throughput can be high, and in our test, if we do not do any restriction, just light the promotion allocated pages until the mini watermark. I found sometimes there will be even memory allocation failure. Okay. So about the hot problem, when we scan the page table of the processes, we will record the scan time for each page. So later, when the page is accessed, we will calculate hint page fault length, where subtracting the scan time from the access time. The lower the length, the more possible the page is hot. So if the length is less than the hot threshold, we will consider the page is hot and try to promote it. So to record the scan time, we use the NUMA balancing bits in struct page flags, which is previously used by the original NUMA balancing to check whether a page is shared by multi-socket. So in this solution, we can only identify the hot pages in PMEM and promote it to DRAM, but we will not reduce the cross-socket access to PMEM directly. But after we promote the PMEM pages to DRAM, we can still reduce the cross-socket access to the DRAM pages. So to how to determine the hot threshold, we use such a algorithm. So for example, if we restrict to promote only 100 megabytes per second, we will adjust the hot threshold automatically so that the total size of the hot pages identified within 1 second will be less than 100 megabytes. The original.
I have a question about the previous slide. So the PMEM access, so this is specific to PMEM, and PMEM access is not, the PMEM access type might not be uniform. Writes can be much slower than reads, right? Is there any consideration to that, to the what kind of access it is to the PMEM?
Yeah, you mean the read write different between
Yeah. So, for example, if page is written, it's more expensive to write to PMM, and it makes more sense to prioritize that page promotion compared to reading.
We're considering about that too. The straightforward solution is to use different hot threshold for read and write. For example, we use looser or larger threshold for write. We can do that, but it needs some tuning. We have a basic idea, but we still have more work to do to make it really have the promise. Yeah, because the read write can be identified by we can identify the page is read or write, where the page fault. So we have all the information. We may work more on how to do that. So the original new balancing is for mapped pages only, but for the unmapped file pages, in fact, they are accessed via some syscall. So we can hook these syscalls to record the access time. So we can then we can calculate the access length where subtracting the last access time from the current access time. This length is comparable with the hint page fault length we defined for the mapped pages. So we can share the same threshold adjustment and the rate limit code between the mapped and unmapped pages. So now we have the basic demotion support and the promotion support. They will try to put the hot pages in DRAM and cold pages in PMAM. But after some while, it is possible that even the cold DRAM page are as hot as the hot PMAM pages. Then all our promotion and demotion cannot do something useful. It's just called thrashing between the DRAM and the PMAM. So how to detect this? In theory, it is possible for us to scan the page tables of all processes to use to clear the access, clear and check the access bit. So we can scan multiple times quickly to find out the access frequency of each pages and sort them to check whether the hot pages in DRAM and cold pages in PMAM. But that is the overhead is high too. Another possibility is that when we demote a page from DRAM to PMAM, we can make the page inaccessible, as if the page is just scanned by the new balancing page table scanner. So when the page is accessed, we can calculate the NUMA hint page fault length for these demoted pages and check whether it is less than the hot threshold, so the page is considered hot. So if the proportion of the that the demoted pages are hot to the all demoted pages is higher than some threshold. We can detect that there's some thrashing between the DRAM and PMEM, and we can take some action, for example, to demote and promote less, or make the hot threshold stricter. So yeah, it has better identification between the cold page and hot pages. Well, we also have quite some to-dos for the promotion side. Yeah, now we have sent the basic promotion support patch side to the main list for several versions. Now I think one of the problem is that we still lack enough review for these patches. So I want to ask for your help to review it if you have time and interest for the patch site. We will send out the MF 12-page promotion patch site soon, and as just asked by David Hort, the read-write throughput, read-write performance of PMEM is different, so we may implement some kind of write bears for that. Yeah, we have some idea and we are working on that. And Tim Chen now is working on the C group based DRAM partition now. To play with it, we have an experimental kernel put on this Reaper. It has the basic support and some other optimization we are testing now. The build and configuration instruction can be found in a README file in the Reaper. We also do some evaluation to our solution. Use a 2-socket server machine with DRAM and PMEM. Yeah, we test it with PM bench and FIO. You can find that with our solution, the benchmark score can increase quite some. Yeah, so the basic, so it works quite well, I think. Yeah, we have some detailed test result. Yeah, if you we will run out of time. So if you have interest, you can take a look at the slides by yourself. And we also have some animation, but it cannot be showed here. You can find it in our in the LPC website. So yeah, I almost ran out of time, so I will not go through the rest of the slides. So do you have any question?
Yeah, Dave was kind of hinting that you already did an evaluation of user space solution. Do you have a pointer about where we can find the details? How does it compare with Autonoma Falls?
Yeah, I'll say, since I mentioned it, a lot of folks have tried this. We actually had code to try these things. I don't see any problem with us releasing that. We probably could. It just stunk. It didn't work very well, so we abandoned it. So if anybody wants to see our horrible, stinky code, I think we probably have no problem throwing it out somewhere, maybe even as a kind of test program. There are also folks that are looking at doing this a little more, I don't know, I'd say professionally. So I will And that's inside of Intel right now. But I'll encourage folks to.
Yeah, one of the thing I was getting to was the comparison, right? I mean, why did it suck, right? I mean, because Numa faults also is expensive because we are taking page faults, right? I mean, so, and then the demotion actually makes sense when your DRAM is fully occupied, right? So we ideally want to kind of detect, we would mostly end up in a scenario where DRAM is full, right? And we want to migrate hot. I got muted automatically. I'm not sure whether you're able to hear me.
We can hear you, but unfortunately we've got to the end of the session. So if you guys would like to keep on talking, you could arrange to meet in a hack room in the chat. But in the meantime, I think I'm going to go ahead and throw up Paul's slides, who's our next speaker. Quick here. Okay, I'm just going to give presenter to Paul right now. And so we have our next talk here with Paul and Matthew about CAT PROCPID maps, what could possibly go wrong. And you can start whenever you're ready.
All right, thank you very much. I'll go first to hand off to Matthew partway through here. You know, a lot of things in a lot of different deployments do a lot of monitoring of proc files, and that's wonderful, but there are some disadvantages. One thing that we've seen at Facebook is we'll have a monitoring program that's confined to a very tiny slice of the system. After all, the point of the system is to run this CPU-bound application. All right, and so yeah, the idea is the monitoring thing gets what time it gets when it gets it, and it reads /proc/pid maps and hands back the information to the overall scripting that controls things and monitoring or Kubernetes or whatever you have, and life is good. The problem is that this little monitoring script or program or whatever it is might be preempted holding nmap_sem. And that's going to block address space changes in the CPU-bound application. In more detail, so we've got this monitoring application, requires nmap_sem. It's going to read procpid as maps, and it gets preempted. Or perhaps it runs out of CPU time in its container or whatever it's in. And then the CPU-bound application has a thread that invokes mmap, and that's going to block because it can't write acquire nmap_sem. All right, well, you know, that doesn't happen that often. Maybe it's not a problem, but the same application, some other thread takes a page fault. And that could be any thread. Now it's going to read acquire nmap_sem. It doesn't need to write acquire it, but because we have fairness on nmap_sem, it's going to block because there is an outstanding writer. Somebody's read holding. The read holder prevents the writer from acquiring the nmap_sem, and now we can't reacquire it either. And if other threads and other unread work consume all available CPU, the monitoring application is not going to run very quickly. All right, and this means that threads A and B are blocked for a long time. Indefinitely may be a strong word, but for a long time. All right. And this happens occasionally across a large number of machines naturally, which, you know we have a problem, but it's kind of nice to have something that doesn't require 100,000 machines for a couple of weeks to be able to test your fix. So I put together a reproducer earlier this year, and it's fairly simple. You have a process that maps a huge region and then maps and unmaps 4K chunks of it. And another one that repeatedly scans procpid maps, and a bunch of other ones that do nothing but consume CPU. And on my laptop, this will cause problems within a minute or so. And the URL at the bottom is the GitHub address for it. Some people would argue this is abuse, and maybe they're right. On the other hand, it does reproduce the bug quickly and allows us to test fixes and also do debugging much more readily than we could otherwise. In addition, like it or not, in my experience, if my software can stand up to some substantial abuse, life is a lot easier for me. But I'll let you guys decide what you want to do with your software. Anyway, if we run this 24 runs. This is on 5.4, which is what happened to be on my laptop. And as you can see, the nmap unmap latency gets really, really bad really, really quickly with a fairly small number of busy tasks. This is on a 16 CPU system. All right. And when we have 1,000 of them, most of them hang. And hang is, again, kind of a strong word. That just means that they were stuck when the test ended. Presumably, we've got a completely fair scheduler. Eventually, they would run, but yeah, as you can see, 12 seconds they haven't. So as far as most applications are concerned, 12 seconds being stuck is equivalent to a hang. Anyway, so I hope I've convinced you there is a problem. It does happen. We've seen it, and I've demonstrated we can reproduce it readily. With that, I would like to hand it over to Willie to talk about a potential solution.
Thanks, Paul. So as Liam is going to talk about in the next session, he and I have been working on, mostly he, to be fair, have been working on a new data structure to store the VMAs in. Right now they are stored in a red-black tree, and the red-black tree is protected by the nmap sem. The nmap sem protects a lot of stuff, really, really a lot of stuff. And so part of what we're trying to do is split the stuff protected by the nmap sem into being protected by other locks. And Liam's going to go into a lot more detail later about exactly how we do that, but the upshot for this talk is that the VMA tree is protected with a spin lock for writers. But on the read side, we can use RCU. And as Paul can tell you, RCU solves all problems. It creates a few new ones, but it does solve all contention problems because there is absolutely nothing to contend on. So one of the things we need to do in order to make that work is to free VMAs through RCU. That's fine. Paul put in some fantastic infrastructure to do that. That all works. That's not a problem. It does allow some new, well, not new. It allows inconsistencies to appear in reading the VMA tree. So are they acceptable? My answer is yes, obviously, otherwise we would have gone a different route with this. But I think it's worth talking about what kind of inconsistencies we currently see and which ones we're going to see. So it has always been possible to see to see a tree, to see a list of VMAs by looking at prop PID maps, which are not entirely consistent with each other. First of all, there's no lock being held. So if you take it, well, even with the lock being held, you're not holding a lock in user space. So by the time you get back from calling prop PID maps, it may have changed. So that's just stale, right? That happens all the time. The second thing is that maybe you didn't allocate a large enough buffer in user space in order to store all of the textual representation of all of the VMAs. And in that situation, we will take the nmap sem, we will read the first chunk, we drop the nmap sem, return to user space. User space says, oh, I haven't got it all, calls read again, grabs the nmap sem again. Now, of course, between the dropping the nmap sem and requiring the nmap sem, the VMA tree may have changed. You may have called nmap or munmap or something else. And so you may see an inconsistency if you have to do multiple reads. That already happens. So applications should already be prepared to cope with the possibility that the VMA tree that it sees, that the list of VMAs it sees is not entirely accurate. If they're not, well, bad news, because that's about to get a whole lot worse. Now that we're holding no lock at all, well, we're using the RCU lock, so we know that nothing's going to go away underneath us. We may see, for example, we may see if two VMAs are created, we may see the second one being created, not the first one being created, even though we know the first one was created first. Oh well. If we call munmap in the middle and then create and call mmap, we might see two VMAs which overlap. That might be something that you end up seeing. For a monitoring application, this clearly doesn't matter. If it's for some other application, well, it could have seen that if the read stopped halfway. So I'm asserting that the new inconsistencies that can be seen or will be seen more frequently are not new. But reality may intervene, and we may have to we may have to do that. We may have to make some changes. So actually, I should take this question. Well, Paul's answered it on the chat already, so I will. Yeah, absolutely. So yeah, at that point, we've already output some of the information, so we can't, we can't produce. We can never actually say this is definitely it. We can make some assertions. We know that the iteration will eventually terminate. We're not going to jump back to the beginning and start re-showing things we've already shown. We are going to go through the address space in order, and if the application detects, oh hey, there was some change in the middle, and this is, I have a state that can never have occurred, it can go back and reread it. That would be something else that the user space could choose to do. Yeah, I agree with Jan. We will generally go with slightly inconsistent outputs, and if some application is broken by it, we'll have to come up with something better. Absolutely. Yeah. I mean, we don't break user space, and we'll do our best not to. So we did some performance runs. This was a prototype from 8 months ago. Things have improved since. We weren't able to get a large number of busy runs. There were some bugs in the tree at the time. They've probably been fixed by now, but we haven't had time to rerun the tests and redo the data. As you can see, we pretty much have linear scalability on the maple tree. The median number is bouncing around a little bit, but it's all within normal sorts of tolerances. The minimum latency is way higher. Yeah, so don't read too much into the precise numbers that we're seeing here. We've done some fantastic optimization. Well, Liam, frankly, has done some fantastic optimization since, and he's really been driving down the cost of the maple tree. And I mean, this test did show, one of the things we got out of this test was, oh look, that minimum number is way too high. Like it used to be, 10% of what it was. But yeah, the scalability is what we were aiming for here, and as you might expect, using RCU means you have essentially flat scalability. The data structure is also more cache efficient, so we have much better sharing between CPUs on a cache line basis than the red-black tree did, because the red-black tree will tend to invalidate cache lines across all CPUs as it adds and deletes things. The maple tree will do that much less frequently. But obviously, this is not ready to merge. One of the problems is, obviously the maple tree itself needs to be in a fit state to merge, and it certainly wasn't back in January. I think we're getting pretty close now. But it's not just proc-pid maps which is covered by this. In fact, I believe the Facebook monitoring script does not in fact use proc-pid maps. Proc-pid maps is easy. It actually uses S maps because it wants to know exactly how much memory is resident. It doesn't want to just know how much is mapped. it wants to know how much is resident in each process, because that's the function it's doing. It's trying to figure out how much memory is each process taking up. And so it doesn't use prop-bit maps, it uses prop-bit S maps. And the tricky part with S maps is that it walks the page tables. It doesn't just walk the VMA tree, it also walks the page tables. And in order to walk page tables in RCU mode, we need to RCU free the page tables as well. Now, we already RCU free page tables under some circumstances. Some architectures require it, but x86 doesn't. And x86 will require it under some circumstances. I think with certain hypervisors, it does it. I haven't looked at this in a little bit. I looked at, you know, what's it going to take, and I saw this huge mess around, oh, we will RCU free page tables sometimes, but not others. And so I think there must be a performance hit to always freeing page tables under RCU, but I don't actually know. I mean, I'm just assuming that someone's gone to the trouble of putting in 2 different ways of doing things, so there must be a reason to do it both ways some of the time. So I think what I'm really asking for is, does anyone know the page tables, and what the performance penalty will be for what the performance problem will be if we just always RCU free page tables. Anyway, this is basically all the talk we have, because kind of hoping for discussion, debate, people saying, oh my god, we need this right now. I mean, is it just Facebook who cares about this?
I will say that MF and scalability is a big problem in a bunch of workloads that we've tried over the years. So it's really cool to see progress here. So I think there's a lot of people that would get benefit out of this. I think people today just kind of avoid it in general. Like they simply will, you know, like not do MAP as much or do it in bigger chunks to avoid this. So it'd be nicer not to have people like work around it in lots of ways. So I think it's really cool to do. And as for RCU freeing up page tables in x86, I turned it on unconditionally once. Nothing fell over, so we can at least explore going to do it more widely. I don't think it's a big problem, whatever it is.
PowerPC has done it for a long time, and they have fairly big machines. So hopefully, on the other hand, they have much more restricted workloads. So I guess the potential problem would be is if there's some strange workload that hits x86 but not PowerPC that cares. I have my doubts given the large size of PowerPC machines, but
it's the kind of thing, Matthew, we could also just go turn on and do some big 0-day runs and see what changes and see if anybody would notice in there. So I have no fundamental objection to just trying it.
Well, that sounds like a fantastic idea. Thank you.
One potential concern I have about RCU freeing page tables is with the accounting, as like how do we account with page tables that have been freed but not really yet?
That is, we've called free, but RCU hasn't run yet.
Yes.
Presumably this was answered by PowerPC.
Well, I mean, I think you're talking about like the per MM page table counters that we have, right? We take that into account when we're moving, for instance. And you're saying if we RCU free them, then there's a gap between when we decrement those counters in the MM and when the memory actually becomes available to somebody else.
Yes.
Is that the concern?
Yes.
I think it's a problem, but I think it's a generic RCU problem. So I don't think it's really specific to this. It's like anything that you RCU free like is not available as a page immediately. So I don't know, maybe Paul can talk about that. Do we do anything on the page allocator to make sure that things happen faster to get freed? I don't know.
There's a bunch of forward progress stuff in the RCU grace period thing. There needs to be more, but that would be one concern. Is that if we have something that's just churning page tables like crazy, we're RCU freeing them, that means more latency while it's being freed, and so potentially there could be an issue. But again, we have architectures that do it and haven't had a problem. So it would be really great to try it. I really like your idea, Dave, of giving it a try. Or did I miss the point of the question? I was typing while you were starting it before I realized it was for me.
I think you covered it, Paul.
Okay. Don't all talk at once now. I guess one thing that might be worth bringing out if people aren't looking at the chat is an issue that Alexander Graf mentioned, which is, shouldn't a process be able to be guaranteed to see its own stuff consistently? My personal opinion is, as Matthew said earlier, that's not guaranteed right now. I mean, if you do 2 reads, you drop the mmap stem in between times, you see inconsistencies. For it to get that, I think it really needs to expect that it has to shut down other maps and unmaps if it wants to see something consistent. But that's my opinion, and I don't claim to be an MM guy.
I think all you said that works now. Awesome. Okay, we can move this discussion over here then. So you're basically saying there is no issue as long as that process doesn't do, in any of its that doesn't do any mmap or unmap, which I concur with. I don't know if anybody out there is expecting it. So the only occasion that I remember where a process was violently and like super adamantly introspecting maps, and it wasn't ASMs, it was literally maps, was the Java runtime. I don't know why, like really, I haven't dug into the code on why exactly you would do that. I only implemented the conversion routines in QEMU to make sure that it actually could do that even in user space simulation. But it wouldn't run without looking at its own maps through the eyes of proc-self maps. I don't know if it does that under an MM lock internally where it just says, I cannot do any maps meanwhile. This is a user space API, right? Like, did we do any guarantees? Did we provide any guarantees that we would be breaking with this? That's, I think, the main concern.
Is it possible to do something like run a test with some of those Java applications with a prototype of this code and see what happens?
I think it makes much more sense to just. I think it makes much more sense to just grab a Java expert and like look at the code and see what it does.
Okay. Yeah, it works for me.
Assert whether this is sensible or not.
I mean, for debugging, you could also just output junk. I mean, we could, as a debugging option, just output junk in there that we think is possible that this would generate, and then see what breaks. We could make it, as worse as we think it will, as bad as we think it will happen, and then, turn it up a little past there and see what breaks.
Yeah, good idea. Chaos monkey mode.
And Alex, the other Alexander says that ProcPid SMaps is often read in 4K chunks, and that it often splits things up as a result, or does multiple reads as a result. I don't know if that applies to Java, but that'd be another good question to ask the Java experts. Are you willing to do that, Alexander Graf? Ask them.
To ask a Java expert, I can try to find some internally. Yeah.
I think there's a limit inside the kernel right now, and it will yield the lock returned to user space and how to be recalled again. So it is possible that if your map is big enough, you're going to get multiple locks and unlocks, and thus a possible inconsistency today.
True. Okay. I'll just ask either it's a bug in Java anyways already then. And I think I have seen that behavior before where we ran across the 4K boundary and then had to like improvise. Yep, I'll ask.
Thank you. Thank you. That'd be really helpful.
So if you think about how it works right now, and it'll be kind of a bit different, like Willie said. Basically, when it reads, it will read up to the boundary and return what it's found, and then continue from the address where it stopped. So when it continues from the address where it stopped, you could potentially hit today. You could potentially hit something that doesn't make sense to the end of the previous entry. What this change would potentially do is basically the same thing, actually, because we would take the RCU read lock and get the 4K chunk and then return it. So there could potentially be an inconsistency in the next call. So your snapshot will be split. If you think of it as windows into what the system has, you'll either get one segment that is consistent and then the next segment that isn't, or you'll get a full consistent snapshot. Does that make sense?
Well, if what you're saying is accurate, then the RCU changes wouldn't change anything, right?
Yeah, I don't think they will. I think. Yeah, I don't think they would.
Right? Think about it, right? Think about it from the MapleTree point of view. You've got, you grab a node, a leaf node out of the tree, and you read out of that leaf node. But somebody else grabs a spin log, comes in, changes what's in that leaf node while you're reading from it.
Right. If you're in that leaf node, then that leaf node will be RCU freed, right?
Yeah. Right.
Right. So that leaf node is fine. So the only, yeah, if there's a large churn of data, then it might be possible that, yeah, there might be something. If you have an RCU read lock, though, yeah, I think there might be. You're right. There could be inconsistencies across chunks within the chunk itself.
Yeah. So you're going to keep making progress because you're going to keep iterating. You're going to keep going next, right? So at any point, even if you have to hit a restart point and go up to the top, you'll be continuing from the end of the VMA that you just started from, but you might end up in the middle of a new VMA. So you might see two VMAs which overlap each other slightly.
Right. So I guess the only worry is if the application is assuming the entire return is consistent and then just checking the intermittent portion, versus you would then have to scan through to make sure that there's no VMAs that don't have some weird overlapping. There's also probably no way to know that there was a gap missed.
Right.
It's kind of a interesting question. I mean, in some sense, outputting overlapping stuff gives the application receiving the data a very clear indication that it's inconsistent. The other approach would be to try to adjust. Say, okay, last thing I output into here, so there's the thing that started here. I'm going to cheat and say that it was shorter and started later. I'm not sure which is worse. My guess is that letting them know that it changed by having the overlap is probably friendlier.
Yeah, I'm kind of surprised that something's going in like this to get this information.
It's a common thing, it seems. Dave Hansen notes something on the chat that's really important, and that is that it might be good for us to document everything that can happen now and what can happen in the future with the RCU reads. And I think that's an excellent point.
I think it might be better to document this as things we guarantee, and that is if a VMA was present before you started the read and remains present until after the read is finished, we definitely show it.
Yeah, if it if it disappeared in the meantime or appeared in the meantime, you might see it or not. Go ahead, Liam. Sorry.
Yeah, sorry. Yep. At the current time, though, like if you use this file and then use the information in this file to do a map yourself, there's no guarantee that someone hasn't come in and done something to the map in between those two times, right?
There's no guarantee. There's other uses for it, though. One use is, for example, to look and see how many huge pages you have. Another use is to just see how much memory is being consumed, right? You know, so there's a lot of different uses for it. I'll just throw out those two because I remember them, and I don't want to. And we're at the end of time anyway, so we should probably be respectful of other people's times. Thank you all very much for the feedback and the suggestions, and especially for the offers of help. Should be exciting.
Yeah, thank you.
All right, thanks very much for the talk and all the discussion. We're going to go on a break now for 15 minutes, and we'll be back with Liam's talk on MapleTree. poll shows we have about a third of the people back from the break. Yeah, we can't do that. Another minute to get back, I think.
Welcome back, everybody. Now we have Liam, and we're going to continue some of the discussion around the maple tree. I'm going to set you to presenter, Liam. I actually don't see him.
If Liam doesn't show up, I can take over.
Sure. All right, I'm making you a presenter, Willie. Thanks.
No problem. Liam's been suffering through flaky internet recently, so that may be what has happened. Okay, so the maple tree. Liam and I have been working on this project together for a couple of years now. The division of labour is mostly that I came up with the initial idea and Liam's done all the work. And somehow he still thinks it's worth putting my name on the slides, which I'm quite grateful for. We do talk about it all the time. A little facetious. So what is the maple tree? It was kind of invented in a fairly ad hoc manner, and then it became apparent that what I'd really done was reinvent a B tree. So now we're just calling it an RCU safe, range optimized B tree variant. If you look at the classical literature on this stuff, you'll see there's some things we don't do. A lot of the literature assumes that you're storing single values, and so it is optimized for that. Our primary target has been the VMA tree, so we naturally want to store things which have a range. So something that starts at a particular address and then continues for a certain number of pages. We are optimized for dense, so VMAs which are adjacent to each other. Some of the address-based randomization stuff will try to spread the VMAs throughout the address space, and that's not great for a tree. It's not the end of the world, but it's not the perfect solution. So how we've done that is that we encode these things as start followed by pointer, and so the length is implicit because the next start minus the start of this one is the length. So instead of storing a start length pointer treble, we store a duo, just start and pointer, which means that if you have a gap, the pointer is null. And so we've got an illustration on this diagram here that you can see on the side, showing a one leaf node and then a few parent nodes. Compared to standard B trees, we have quite small nodes. We've done that for a number of reasons. The classical B tree is to handle storage, and so you want to read in from disk, 4 kilobytes or 256 kilobytes at once. But we're dealing with memory, and so we are dealing with CPU caches. And so we think a smaller node is better for us. That's an assumption which is going to be tested. We actually started out with 128-byte nodes and decided that was just too small. So we ended up going to 256-byte nodes. We also have the ability to search the tree looking for a gap that is at least a particular size. And again, this is for the VMA tree, so that's why we added this feature. When you call mmap, you are saying, please find me a gap that is at least this big, somewhere that I can put this mmap. And so to avoid scanning every single node in the tree, we cache at each node. We cache the size of the largest gap in any node below that one. So you can see we've got 30 stored in this one, and you see that node has 25 in it, that one has 30, and then we could go down again, and you can see that this one has he stopped putting it in, but yeah, the size of the largest gap anywhere in this tree is 30. Yeah. Obviously, the primary thing you do in a VMA tree is you look up a VMA by address. So that's obviously what it's optimized for. One of the pieces of functionality we added is bulk loading. Things that again don't really come up in the literature is when you're if you do an mmap which covers. So you do an mmap map fixed, which covers a large range, or you do an munmap of a large range, you end up having to bulk delete a lot of entries, and that causes us a certain amount of pain. I don't know. It's something that doesn't happen terribly often. Obviously, there's the bulk delete of when the process exits, you actually want to delete everything from the tree. But it's relatively rare, but it does happen that applications can call munmap of a lot of VMAs all at once. Very much depends on the application. So locking, we talked about this in the last session, but for those who weren't in it, we protect with a spin lock. The patches that you will see today do not move anything out from underneath the mmap SEM. The mmap SEM is still there, and so we're actually just adding the spin lock. So readers will continue to take the mmap lock, and it will be in follow-up patches where we start to actually move things out from underneath the mmap SEM. The object here is to the object for the first set of patches is to get the maple tree in because the maple tree is an independent data structure, right? It's not just going to be used for VMA trees. It's going to be used for a whole bunch of things in future. I have all kinds of plans for it, but I don't want to talk about it in this session because we don't have time for it. But the maple tree is an independent data structure, and then someone's put that in and convert the VMA tree to use it as the first user. So we are looking to show performance wins simply from replacing the data structure, and then we will optimize the locking in follow-on patches. Yep, and we are also going to have our own. We're going to have new iterators for VMA, so much less of this calling VMA next and following chains of VMA pointers. We're actually going to we actually treat the tree as a grown-up data structure, and we iterate over the contents of the tree using a maple tree iterator. So, okay, I misremembered Liam's slides. Yeah. Okay, so Liam wants to talk next about what the RCU future looks like. So once we're moving stuff out from inside the mmap SAM, how do we make this work? How do we take advantage of this? So for readers, so one of the primary things that we have to care about is the is page faults, right? I think everyone has probably felt the pain of dealing with page faults. It's not just Facebook with the with the monitoring workload. Having every page fault take the mmap SAM, I mean that's contention on a cache line, right? And we really do have applications with thousands of threads, each running simultaneously on CPUs, all taking page faults at the same time. This is a real problem. Even on my laptop, right? I mean, I've got Firefox running right now. It is presumably taking a lot of page faults. I'm not monitoring it at the moment, but I have in the past, and it takes a lot of page faults and a lot of threads all at the same time. So we have a prototype where we will simply take the RCU read lock in order to take a page fault. If it's a minor page fault, that is enough. If it is not, if we need to actually allocate memory, and particularly if we need to do I/O, or we need to call into a file system or a device driver, we are adding a reference count to the VMA. And that allows the file system, so we take a ref count. So this is a slow path, right? The first path we already dealt with. If there was a page that can be added, that all happens onto the RCU lock, and that's fine. If we need to sleep, we take a ref count on the VMA and we drop the RCU log. And then we call into the file system or device driver, whatever, and it maybe does I/O, maybe it allocates memory by sleeping, it doesn't matter. The protection that it was guaranteed before by having the mmap SAM held is that the VMA was not going to go away underneath it. And we've got a ref count on the VMA, so it can't go away underneath it. And that it could sleep, right? If you're holding the RCU read lock, you can't sleep. So we drop the RCU read lock before we call into the device drivers. So from the device driver point of view, or the file system point of view, nothing changes. Liam, you're back.
Hello, can you hear me?
I hate your ISP so much. Dave Foothouse says he can't hear me. Okay, has this been silent for everyone the whole time?
We could hear you.
Oh, okay. Great! I could hear myself, and that's it. So that was awesome. Hi, everyone. Sorry, I lost internet.
So I've been doing my best to run your slides for you. Do you want me to just keep going, or do you want to start talking at this slide? And
no, go ahead and finish this one. I'll take over the next one if you.
Okay, that works for me. Sure. Okay, so that's how page fault is going to get handled. From the writer point of view, we are going to need to, well, one, if we're deleting a VMA and there's a ref count held on it, we need to sleep waiting for that ref count to be decreased. So it's not quite a plain ref count. You know, we need to also sleep on. That's going to be a fairly rare operation, right? Applications do not generally unmap the VMA being used by one thread from another thread. That tends to lead to SIG faults. I mean, it does happen. There are some strange applications out there that do this and then handle the SIG fault and blah, 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 blah. Yeah.
Actually, there is a little of wrinkle there because of the way we like the application may have two different areas that have been merged by the kernel as one VMA. And so, yes, the application will not unmap the space where it is faulting, but it might be unmapping an adjacent space that has been merged into the same VMA by the kernel.
Yeah, that is possible. I think also there's a possibility of other threads looking at it if it's a shared VMA, but those are pretty rare things that yeah, you'll have to work around. The merging, you would basically be faulting something while someone else is mapping, and then they have to be connected either by start and end or end and start to be merged. Those are definitely corner cases that would need to be looked at.
Thanks. Yeah, but I do want to remind you that we only actually take the VMA ref count in the slow path. So both the reader has to hit the slow path and the writer has to unmap it at the same time while it's presumably blocked on I/O or something. So I hear what you're saying, that there are times that this is going to happen, but I still think it's going to be fairly rare for it to happen. What else did you want to say here about forking? I don't think I fully understood that.
Yeah, so the RCU feature, basically, right now the way the forking happens is we lock the old MM and the new MM, and we copy over information back and forth and duplicate the VMAs, and then we unlock it. In the future, what we're thinking is we could lock the old tree, duplicate the tree, and then unlock the old tree, and the old tree it will never be used again. And then just use the new copy to iterate through the VMAs, copying them. So basically you increment the ref count through all of them, and then you decrement as you go through and make your own copies, or you delete it from the tree if the VMA don't copy flag is set. That was kind of the part I was thinking of there.
I guess I have to do the next slide thing for you now.
Oh yes, performance. So I did want to put in one slide on performance because David Lohr did put in that this was about performance. So basically, the only thing I really want to say is right now the real world workloads are pretty much not changed. The user time goes down, the system time goes up, and the worst case in the elapsed time on the kernel build is less than a second. So we're getting on par performance is what I would say for real world workloads. The other thing is basically we need. It would be good to identify benchmarks. I think this came up in previous topics. Benchmarks in which we can say, okay, these are the ones to use. I think it was Michelle's, actually, come to think of it. These are the benchmarks we want to target for this particular change, or this particular MM area change, or even the entire MM stuff. Basically, what I've been doing is running through the MM tests sweep on before and after, to see if I can identify anywhere. The big win, I think, in performance-wise is besides RCU and the locking portion, is that right now the way that the tree, because it's an RB tree, you can't just change one part of the tree, right? You have to remove and then re-add. And if you think about that operation, if you're removing a node from an RB tree, so all the colors change and things get shifted around, and then you add it back, and so everything kind of like just gets reverted almost exactly the way it was, except maybe now there's a different interval in between the next or the previous or something. So what I would like to see is is to reduce the modifications to the tree. So we don't need to say, oh, we're removing this piece, so we're going to delete it, and then we're going to re-add it. What we can just do is just write over it and know that we're writing over something, so we get the VMA to free, and then we store the new VMA, and that sort of thing. So there's ways to benefit beyond just the locking, even though the locking will most likely be way way bigger in the performance-wise. So yeah, and there are trade-offs as well with this tree. The updates can be more work. If you're writing a large area, overwriting multiple VMAs or something, it can be a lot of work. The only thing that I've seen that does multiple VMAs is Android, and I think Android does 2, and I think it's the Guard VMA. It has a VMA on one side. I'm not sure on that. Either that or it's because they use CLang, and CLang does something special. I'm not sure if that's actually built into CLang even. So yeah, but sometimes, like I said, the writes can be even less because we don't need to take things out of the tree in that. But the reads do seem to be faster, which is the majority of what the VMA's tree is used for anyways. Can we go to the next slide? Really?
Oh.
You still have control.
Sorry, I forgot.
No worries. So there's other potential users for the tree. Oh, maybe I have control now. There's other potential users. So there's other potential users, the IDA and the IDR. To get there, the tree will need to change a bit. We have to start using dense nodes. Dense nodes is a concept to increase the efficiency of ranges of length 1. Most of the multi-node type stuff is already in the tree. It's just not as well tested, or well, maybe there's test cases, but there's not users, so it could potentially have fallen to the wayside. No, there's test cases, but the nodes have been disabled actually. So we need to re-enable that and sort of figure all that stuff out and make sure it's working well. So that's and then the other user that comes to mind is the page cache. Earlier on, I hope Willie mentioned that we do support searching for gaps. So we would replace the gaps for search marks, and then you could mark where to search in the tree, and also for shadow entries, for pruning the shadow entries. Yeah, so let's see if I can do this. Oh, all right. Well, thanks everyone for being here, and I'd like to open it up for any questions.
So as is, without thinking of any of the performance benefits that having an enabling RCU in the future will bring, at this point you have a drop-in replacement for the RB tree, for the VMA tree, and correct me if I'm wrong, but there's no more added complexity from what the RB tree was doing to what the maple tree is going to do, right? For example, right now we have 3 data structures, basically to like compensate for some of the shortcomings of RB trees, thinking complexity-wise, right? So by having a shallow tree, we can immediately like get rid of the list, which you've done. We can get rid of the cache, which you've done, and basically have one data structure to govern VMAs. I find that really appealing, not even thinking about performance-wise. And correct me if I'm wrong, but we're basically, the worst case scenario is nothing really changes, right?
Yeah, so the only thing, performance-wise, nothing really changes except for maybe was it there's one benchmark that was not as great. But the added complexity comes with the locking right now, because it's in the future, the way that we want to lock is reversed, right? We don't want to have the mmap guarding everything. We want to have the maple tree lock guarding the edits to the tree. So once we change, because we have an RCU data structure, to edit that data structure, you have to take the spin lock or take an RCU read lock, and you can't sleep in those. So because of the way the ordering is, when you're going through and you need to say, oh, I don't know, allocate something, it was not a problem before, but now that's a potential sleep path. So LockDep will yell at you, or RCU checks will yell at you. So I had to put in a lot of these lock-on locks, which is really really unfortunate. And that's kind of probably one of the things people looking through the code will notice, and they'll say, what is going on here? And that's basically why, is because this is RCU, and we have to be technically correct, even though we know that no one will change it under us, because right now it's protected by the mmap lock globally.
I forget, what were the problems with using sleepable RCU?
Oh, I don't remember. Peter really wanted to do that.
Well, I can reply on this. So sleepable RCU, the read side is a little bit slower than classical RCU or other flavors of RCU. However, for the tracer requirements and eBPF, Paul McKinney did a RCU tasks trace, which allows taking page fault and sleeping within the read side lock as well. So it's similar to SRCU, but without all the overhead of the read side. So maybe there are common use cases there to look into.
I really want to avoid adding trace tasks. Fixes it.
Sorry, you cut out there. Can you repeat that, Peter?
I want to see task trace RCU usage until Paul fixes it.
Oh yeah, of course. I discussed with Paul the no arts requirement yesterday, and he's going to put that on his to-do list, on his backlog.
But anyway, I think their problem with SRCU was that there was a lot of gate thread activity for call SRCU.
Well, that's maybe one thing, but the other one is the memory barrier that you have on the read side lock of SRCU, which is slower. So it might matter here for performance.
That wasn't their concern at the time.
Okay.
It might be like, it might reduce complexity for the sake of a barrier. I don't see that to be too bad.
Yeah, and I guess the other thing about it is we need to figure out what needs to change for VMA locking as well, and try and do it all. Try and do it so that we don't step on each other, or we don't change too much in the area at once, because Michelle is also working on the SPF stuff, right? So. Ideally, we would have the SPF come in as well as the maple tree to just make things much quicker.
So I actually have comments on that regarding the page fault pass and the thing we were discussing, like if there's a page fault that takes a reference and we wait for that. I really feel that I'm not super comfortable with that, and I don't have a full solution for it either. But I think it would be really nice if we had a way to completely sidestep that issue by being able to do some speculative page fault. That is, we would not do anything that prevents a write-off from occurring, and then at commit time have a precise check to know if there was an interfering vital or not. And if we could get something figured out that does that, I think it would be a lot better than still having edge cases where we have reader vital interference when they work on things that are not actually the same part of the address space.
So I did get a BOF at it, so we can discuss the locking for tomorrow.
Yes.
Because we're probably going to run out of time.
How much time do we have? Because I can take this if.
Yeah, we're actually at the end of the session, so the
Okay.
box sounds like a good idea.
Thank you.
Yep, thanks
All right.
guys for. Yep.
Thank you.
Thanks, Liam. Okay, our next talk is from Pasha. This is about preserving state for fast hypervisor update. I'm just going to present it over to him right now and get his slides up. And I think everything should be ready, so you can start whenever you want, Pasha.
Okay, just let me see. Okay, now I can change the slides. Okay, so in this talk, I'd like to give an introduction in a way to do fast hypervisor update with the mainline Linux and available VMMs. And also, I'd like to discuss about the way to preserve the state across the reboot. So during the hypervisor update, we have to preserve state of the running virtual machines, devices, and some other related data structures. And there is no convenient way to do that currently, but I'll show the way it is done, like at least one of the way how it can be done now and why it's not ideal. So this is outline. We'll talk about what is fast hypervisor update, why it's needed, compared to alternatives. Then I'll show a small demo. I'll talk about a little bit. I'll show some data using QEMU VMM, and then the discussion topics are going to be how to what is currently used and how that can be improved. And for the future improvement, I'll also briefly talk about the multi-root update. So the hypervisor update is important because cloud relies on virtualization, and cloud being a shared environment, we cannot really shut down the VMs to do the regular reboot and like the traditional update of a server. We have to have the downtime for the VMs as short as possible, and ideally the VMs should should resume after the update from where they were paused. So shutting down the VMs is not an option. And of course, the reasons for updates are well known. It's security, functionality, performance, stability. All of those are important for the availability promise which cloud vendors are giving. So there are two alternatives which provide a way to do a fast hypervisor update, and I'll talk briefly about these alternatives. One of them is hard patching. So hard patching is a very good method to fix a zero-day security issue, but it's not an update strategy. You cannot really update to a new version of kernel using hard patching. And hard patching also adds a lot of other complexities and limitations, which I listed here. So, and another one is live migration. Some cloud vendors today use live migration as a method to do the upgrade. So it can be used, but it is slow, and it also increases the network load. And it's unpredictable in terms of how long it will take. It depends on the load of the VMs. And there are some other problems with the live migration, such as if device state is large, for example, GPU might have a large amount of memory, or maybe there is a SSD that is attached. It's local SSD. It's just not practical to live migrate it to a remote host. And also the availability of the resources is also needed with the live migration. So the labs must be planned accordingly during the update, that there has to be this backup host where the VMs are migrated to while the current host is updated. So let's go to the next slide. And here's the one example of the virtualization stack. So we have hardware, firmware, host operating system, and VMM. So what is light gray is what we want to be able to update during fast local update. So it's not necessarily just the hypervisor and VMM, but also the firmware as well, if possible, should be updatable during the reboot while virtual machines are suspended, or like maybe some other means preserved. These are some of the recent publications and talks about fast hypervisor updates. So it's a hot topic right now. And there have been some talks about fast hypervisor update in KVM form, but I wanted to bring it to Linux Plumbers because the way to preserve memory across the reboot is more related to kernel. So, okay, so how can we do the fast local update today? The building blocks for that are the following. kexec, which in general provides a way to do a fast reboot. We skip the firmware, so no time, we don't spend time resetting the memory, resetting the devices, and we don't spend time during the firmware reset. And also kexec enables a way to preserve memory across the reboot on any server. So the second building block is the local live migration. So with the regular live migration, we migrate the VM from one host to another host, but it is also possible to migrate the VM to a file. But and another thing is that it's also possible to snapshot the VM. So if VM has a virtual hard drive such as COW2, it can be snapshot right into the hard drive itself. But with the local live migration, normally we also, like with the regular live migration, normally we also copy the VM pages, but we don't want to do that if we do it locally, because it's just too expensive, and it's basically we have to copy all the VM pages maybe to a slower device before the shutdown, and then bring them back from the device after the boot. So we want to keep VMs in memory. So, and to do that, we use PMAM, DEX, and DEX-enabled file system. So PMEM is actually emulated. It's not a real PMEM. So we use a regular DRAM and just specify that this part of the RAM is actually used as PMEM. So across the kexec reboot, it's preserved. Then on that, then we convert that PMEM into DEX device, and then we put a DEX-enabled file system on it. And if we allocate if we create a new file and map that file on that file system, we don't use page cache. We do not use double memory. We just use that file directly. And that's the way we start virtual machines. We start virtual machines with their memory presented as files on this PMEM-based DEXFS-enabled file systems. And when we do the live migration, we simply skip the copying of the memory state. We only copy the devices state, such as CPU registers, or if there are any other virtual devices. So this allows us to do the VM state preservation across the reboot. Let me go to the next slide. Okay, so here I want to show a small demo of all of that in action. So I'll try to share an external video. So this is tested on a host that is used in Azure. I started with rebooting it, so we'll go through the firmware first. So this is the firmware, and it has 256 GB of memory, and it also has Xine 128 Xine threads. So, okay, so the system is booted. I added some text to dmessage just to show the kernel boot time. It was 3 seconds. And the next, I also showed the memory layout. It's so we only have 18 GB for the hypervisor itself, but it could be smaller. The rest of the memory is actually PMEM. So we have 9 GB and 231 GB as PMEM. So this is just regular DRAM, but we used memmap kernel parameter to configure those PMEMs. So, and the next thing, I run my script to start sample virtual machines. And okay, so here we are booting virtual machines. There are 4 Windows virtual machines and 4 Linux virtual machines. And in the bottom right is the console for our host. So if you see SAC prom, that's Windows. If you see QMX86, that's Linux. And after that, I'll run a script in each of the virtual machines, basically to show the time and type of the virtual machine, and it will jump up and down so we can see that there is a progress. So the script is running right now, and we log in into Windows, and Linux login was passwordless. So yeah, so we have Windows, Linux, intermixed, and all of them showing time. And the next thing, I'll do this fast update, which is basically snapshot all the running VMs and then reboot. Okay, so we are rebooting now. It takes, I think, a little less than 5 seconds to do the reboot. And now we are back, and all the VMs attach and continue running. My Tmux script was a little bit messed up, so the console now is top left instead of bottom right. But you see the uptime is 0 minutes, and then the boot time for kernel was 2.7 seconds because this was kexec. It's a little different compared to the cold boot. So this is it for the presentation, for the demo, and I want to get back to the slides. So, okay, I'm trying to figure out. Daniel, do you know how to get back to the actual slides?
Yeah, let me try something here.
Okay, good.
And I'm going to make you presenter again as well. Okay, you should be all set.
Thank you. So that demo was using Cloud Hypervisor. It's a Rust-based VMM. The same can be performed using QEMU. I'm not going to show you the demo, but this is just a data using QEMU and fast update. So on the same server as the previous one, it takes 5.4 seconds with QEMU, and on my workstation, it takes 2.5 seconds. So the next thing is I want to discuss about what we use to preserve memory. So we use emulated PMM, and the truth is PMM works very well because in addition to kexec, it actually can be preserved across the warm reboot if we reboot through the firmware, but the firmware is taught not to reset memory, and also the firmware taught to, so for example, if it's a UEFI firmware, to mark the PMM regions of DRAM to be type 7, then Linux will magically recognize that DRAM as PMM and will use it just the same as if we use the memmap parameter. The same is true for U-boot and device tree. We can do the PMM node, and and ARM firmware can also be taught to do the warm reboot and not to reset memory. And then there is a kernel parameter choice which can be used on any machine, but unfortunately with the memmap we cannot really do the warm reboot. We can only do the kexec reboot, and thus we cannot really update the firmware together during this update. The problem with PMM is that there is, first of all, this is not a real PMM. This is just a regular DRAM that is marked as PMM, and in some parts of the code we even refer to it as a legacy PMM. But it's very useful to do to be used for this kind of hypervisor update. So I don't think that it should really be legacy. But the second problem with this is that it's not portable. So for example, you cannot really expect admin, like when you reserve this number of huge pages, for example, when you do the QHTLB, just say, okay, I need this amount of memory to be reserved as huge pages. But if you want, for example, 90% of your system memory to be used as PMM, you cannot do that using the memmap parameter. You have to specifically tell kernel which part of memory is going to be used as PMM. The physical memory must be contiguous, so there must be like this intimate knowledge about the actual host, and the configuration is not portable to a different machine. So it's not something easy to maintain. So these are the problems with using PMM for this kind of use case. And I just wanted to see if there are any suggestions of what can we use, but still being able to preserve across the firmware reboot if possible, or maybe improve the interface of how we create this legacy PMM parameter. So for example, instead of using this memmap, we would add a new kernel parameter which would just specify the number of gigabyte that must be reserved for the PMM. So any suggestions are welcome.
Oh, I was going to say that the memmap parameter is pretty terrible. We do have the soft reservation attribute now. That at least that one only converts known memory and not just kind of random things.
I think that what you're talking about is this type 7, right? Soft reservation in UEFI, or is it something else?
No, the type is for contiguous stuff. The EFI memory SP special purpose attribute it's an EFI attribute, not a type.
So when we've done a live update for Zen, we've actually not reserved separate memory at all. And the handover protocol that we use for live update in Zen gives a breadcrumb which essentially leads to all the live migration state, which has to be re-ingested into the new Zen, but also essentially a list of pages it's allowed to use. And we do kind of guarantee that it's going to have at least a big contiguous chunk that it can use to get started before it's got a proper allocator. But then it just ingests the rest of the pages into its allocator that don't happen to have guest memory in. And I don't know that I would advocate that. It's certainly not what we do for our live update of Linux. We do live update of Linux in a very similar way of just sort of everything outside
Preserving any pages worries me because of the possible memory fragmentation and issues during boot. I mean, it's really hard to test if once memory is fragmented that the next boot is going to be successful. But what you're saying is interesting too, to have a predefined number of contiguous chunks like guaranteed to be available. So basically have something guaranteed, so we should be able to successfully boot just with those chunks of memory, and everything extra is just added later during boot.
Indeed, yeah. So what we've done is in Zen we've reserved a slot for live update, which will hold at least another Zen kernel and enough of what it needs for its early boot allocations. And then each live update will bounce between those two contiguous slots in memory. I think we eventually did it that way. But yeah, it's not quite as trivial to do that in Linux.
Pasha?
Yes, Kiva.
So, great set of discussion topics. One other topic I wanted to add here, and you and I have talked about it quite a bit in the prior months, is most of the clouds are moving in a direction where we want to project more and more hardware into the guests. And how does this scheme work when we have physical devices being projected, whether it be SRIOV or complete DDA into the guest? Curious to see what other cloud vendors are doing there.
Yes, and I'll talk about that. That's my next discussion topic.
Okay.
Is preserving device state across the reboot, and that's also part of the of this interface. So I would like to use the same memory as we use for virtual machines to be used for the device state preservation. So, but yeah, let's move to the and we can combine the discussions of both of these topics. So, preserving device state across the reboot. There was some work done in this area. So Jason Zhang, he presented this last year at the KVM forum, and I worked with his code and ported it to the latest upstream kernel and experimented with that as well. So that code works with Intel IOMMU, and it doesn't work with any other types of IOMMU, but at least just for the Intel IOMMU, what is preserved is, so we have posted interrupt tables, and then there is some soft data structure for those tables. So the difference between tables and soft data structure is that soft data structure can move so we can actually have a package and copy it before the shutdown, and then recover the package to somewhere else after the reboot. But the tables, they must stay in place. And the same for the IOMMU page tables. So they must stay in place. So we have VMX tables and data structure. We have IOMMU page tables and data structures. Then we have interrupt remappings, soft data structures, PCI, soft data structures, and VFIO PCI soft data structures. So it's really a spaghetti of stuff that we need to preserve to be able to attach back to the device that was directly attached to the VM. Right now, what Jason was doing, he used the PKRAM, which is the next topic in this micro conference, to preserve this data structures and also the fixed tables. But again, at least the fixed tables, they might add the memory fragmentation issue. And alternatively, it would be nice if drivers had a way to allocate page tables directly from the PMEM device. So we would have, from a file on a DEX file system. So where the VM's memory is saved is exactly in the same place we would have the device states saved. So everything would stay together. And that way we could also preserve the device states across the firmware reboots, not only through the kexec, because today only kexec is supported. And I see the raised hands, please. Bill? Velu, you raised your hand. Okay. So, are there any comments about what can be done as a way to preserve the device states directly to the DEX file system instead of using the kernel allocator and just allocating from anywhere in memory?
So what's the minimum that actually has to be preserved? For a start, if you have assigned devices, one thing you can do is quiesce them. Well, maybe, depends on your device, right? And that gets easy because you don't really need to keep anything going during kexec. If you have an assigned device that you cannot quiesce, you actually need to keep all its mappings valid at all times during kexec. So even when the new kernel takes over the IOMMU, you have to do so such that the device will never take a fault. And you can do posted interrupt and point it to an interrupt table and that's all you have. It's not really linked to a running VMCS, right?
That's exactly how it is currently implemented using the posted interrupt. That's right. And the devices which shouldn't be touched during boot, and they have this flag keep alive pest, and that flag is parsed early in boot, and so the drivers would just skip the initializing the device.
Yep. So we have hacks to the IOMMU driver to make it allocate from, essentially from PMEM or from our hacked version of. We're also doing kind of mandatory access control there for managing that external memory, so that we make very sure that one guest cannot get at another guest's memory with, and the access control for that is built into the management system, which we need to sort out and post upstream.
So how that hack works? I'm not aware of that hack.
Which one? In the IOMMU?
Yeah.
Basically, we've hacked a few cases to conditionally allocate from the guest's persistent memory. instead of kernel memory. So the way we do it is we essentially imagine taking a box with lots of memory and booting it with memory equals 2 gig. And Linux only does memory management on the first part of that. And that's why we posted some patches. I was talking about this in the chat earlier about making KVM take just a PFN instead of a struct page for lots of things. So that you can use essentially external device memory, which is fundamentally what we're talking about, except we did it differently. But yeah, we've got hacks to the IOMMU to make it use IOMMU page tables from that same memory. There's a chunk of memory for a guest, and yes, some of that is the guest's actual memory, and some of that same slot is used for the guest's page tables and other stuff that's going to need to be preserved over KExec, including user space gets to store some stuff there as well for its own essentially live migration state from one boot to the next.
Okay, well, yeah, that's interesting. I'll take a look at that and see. And another thing is that VMX would need to be extended as well to save to the guest memory as well. And but yes, if we were able to allocate directly from like the tables, if they were allocated from the guest memory or from the PMEM memory, then the soft data structures, they're fine. They can be passed from one KExec to another KExec or using like the firmware because they're movable. They're not issue here.
So we don't do that in VMX, right? We treat it like a live migration. Ultimately, live update is, I keep thinking of it as live migration in time instead of space. Instead of going to another box, you're going to the same box later. So all the kernel KVM state is serialized. It's all serializable for live migration anyway. So you just user space sucks it out and puts it in the shared memory, the persistent memory, and then consumes it again. It's just like a live migration when it starts up again after the KExec. Now I do have aspirations to get the kernel involved here, because do you really need all those CPUs to do your KExec? Can't some of them still be running guests while one or two of them are off doing the KExec?
Well, that's yes, that's partitioning, yes, and that's what I was also looking into. Basically, do not do the VMX if you have like actual hardware partitioning, and let the VMs run during the reboot without suspending the VMs. I think that it's not feasible today because we do so many VM exits, and but
that's okay, because some VM exits are lightweight and don't take much to do, so you could run those essentially with a run loop. And yeah, other VM exits would be a heavyweight one, and yeah, basically that thread ends up blocking until the real kernel comes back. But I think if you've got decent hardware set up, you shouldn't be taking that many VM exits, and you could get quite a lot running.
I totally agree. So if it's a lightweight VM exit, then just handle it during the reboot. But if not, then suspend the VM or the thread until the new kernel is up. So let's. I also see Dan asking in chat, is PM suspend resume suitable here or not? So Steve Sester talked about this during last KVM, is to have an agent in the VMs to suspend the hardware prior to the reboot and then resume it after the reboot. So that's a good approach. It just relies on this extra agent inside the VM, so it becomes not VM transparent, and also it relies on the workload of the VM, and that VM implements the power management stuff correctly for the attached devices. So that's so it's not ideal. I mean, the ideal solution would be that we are able to do the fast update and not worry about what kind of code is running in the VM at all.
Hey, Pasha. So your last point seems to suggest that the device state should be preserved in the emulated PRAM. So, and then why don't you do it the other way around? You preserve the VM memory in PK RAM instead. then seems to be more flexible than emulated PRAM because, like you said, you have to configure it early
So
during.
the reason why not preserving it in PKRAM is because we lose the ability to do the firmware update with if we use kernel-only data structure. And the second is that the memory fragmentation adds the complexity, the test complexity that we might just fail to boot the next kernel during next boot. And there is a workaround for that, as was mentioned earlier, to have some contiguous memory preserved. But I'm still worried that that fragmentation could bite us elsewhere. So. So that was for directly attached devices. And then we also have virtual functions. So if a device is sliced and we have several virtual functions, how do we preserve the state of such device? So today, all the virtual functions are handled by the hypervisor itself. And there is no good approach to save, and the state of the virtual functions is all in the device driver. So there is no generic way to preserve the state across the reboot without actually modifying the specific drivers for the specific devices. One way to solve that is actually to move the handling of virtual functions to I/O domain. So start another virtual machine, directly attach devices to that virtual machine, and then use the devices from that virtual machine as to handle the virtual functions for the VMs. So again, this is not ideal, but I wanted to see if we could brainstorm about this and see what if there is anything better that we could preserve virtual functions.
I'm not sure I quite understand the problem.
So the problem, yeah, I will repeat the problem again. Sorry for interrupting. So the problem is that with the pass-through devices, we like in the previous slide, when we preserve the device state, we are not worried about the driver itself. So it's just that the state of PCI, VFIO, interrupt, remapping IOMMU, and VMX, these subsystems need to be preserved, but not the driver itself. However, if we have a virtual function, then the driver is involved as well, and we need to have a driver to preserve the state in addition to all of that is preserved for the regular pass-through device.
Gotcha. Or at least in particular, you need the PCI subsystem of the new kernel not to reset it and turn off all the VFs.
Well, that's true too. So the keep alive flag should be passed to like every device in hierarchy to like toward that like last node that is preserved.
Yeah, so for the general case, I'd actually like to be able to pass a packet of arbitrary information from a driver running in the first kernel to the incarnation of that driver that runs in the next kernel, right? And that will accelerate kexec, regardless of hypervisor stuff, right? Fast kexec from one kernel to the next. And it means that the driver in that new kernel will not need to enumerate and reset the hardware and get it into a known state. It can consume the state from the previous driver. or look at it and say, screw you, I don't trust that version of the driver, I'm going to restart the hardware anyway. And that would cover the SRIOV status as well, potentially, right? So we could pass that across from one kernel to the next with all the information about the VFs and essentially the PF driver state.
Well, yes, if we teach drivers about this update, I was hoping we could do something driver independent, but I guess it's not a problem as well. If we are talking about the cloud system, then the number of drivers that need to be supported is actually not that large. So we could actually specifically extend this the drivers only for the devices which are part of the like a specific cloud.
Yeah, I mean there are some that don't really need much driver support in the PF anyway, right? We actually extended VFIO to allow SRIOV on VFIO devices for ours because we didn't need it. But yeah.
Okay, so and the last topic that I wanted to quickly touch is multi-root update. So basically, I've experimented with booting two Linux kernels on the same host simultaneously. So the idea is that you say you have 256 gigabyte of memory. Have the first 8 gigabyte for the first hypervisor, second 8 gigabyte for the second hypervisor, and the rest of the memory is for the virtual machines that are running on this host. And use like being able to pass the running VMs from one hypervisor to another one using the same method as what we do with the kexec. Would basically allow us to do almost instantaneous update of the hypervisor because you sort of switch from A to B partition. And today it's the way I experimented with that is basically I modified the kexec to not to shut down the current system as it's normally does, but instead return. But they start a new kernel on the CPUs which are offline in the current kernel, and use memmap parameter to teach the second kernel about what memory it can use to boot. So that's basically something that is for the future improvements, but I think it has a lot of potential because of this ability to do this.
How did you deal with the devices? How were the devices shared between these two kernels? At what?
Right. So the devices, like the second kernel, shouldn't like when it boots, it shouldn't touch any of the resources that the first kernel uses. But as soon as the first kernel is done, so as soon as the second kernel is like fully booted and is ready to accept the virtual machines, the previous kernel suspends them and tells the next kernel to, okay, you can pick up the work from here. And the second kernel just basically resumes the VMs and the and also captures the device handling for whatever devices were attached to those VMs. So basically, it's very similar to the kexec case. Just we just don't have to wait for the second kernel to boot, so we safe on that.
I guess if we teach drivers to participate in this protocol, then the problem is a much more tractable problem. David was talking about a state packet that could be handed over to the new driver.
Yes, and we can teach drivers. That's good. But again, the page tables, if it's expensive to create those page tables, that's not something that we want to reinitialize, so that whatever the package of information that one driver from old kernel passes to the new kernel, it should be able to also pass this static information that was already allocated for the device, and hopefully that that memory comes from that shared pool of memory, such as PMEM or somewhere else. So okay, I think that we are out of time. So thank you, everyone.
Thank you, Pasha.
Thanks very much, Pasha, and to all the people who participated in the discussion. We'll go on another 15-minute break now, and we'll come back with Anthony's talk on PK-RAM. All right, everyone, it's about time to start up. So I'm going to put Anthony's slides up and let's see. I see Anthony in the room. All right, Anthony, you should have control of the slides, so you are free to start whenever you'd like. Thanks. And I don't think that your audio is working, at least on my side. Let's see. I'm not getting anything.
Okay, how about now?
I can hear you fine, Anthony, now.
All right, excellent. We get some video going here. Okay, start again. Hi, everybody. My name is Anthony Snaga, and I'm going to talk about PKRAM, which we just heard mentioned a few times in the last presentation. Basically, what it is a way to preserve memory pages across KExec. It provides an API for coalescing the data as a stream of bytes or in-memory page data. One example that I implemented in the patches was a way to preserve the data of a TIFFS file. So the page data preserved as pages, and the file attributes preserved as a stream of bytes. Now, what this provides over some other options is flexibility. You don't need to determine a size in advance and can configure physical memory. As we heard about for emulated persistent memory, those things you don't need to know. You can just preserve what you need to preserve. And from the previous presentation, some use cases became clear. Obviously, live update of a cloud hypervisor. This can be used to preserve a guest VM across a reboot, both its data, guest memory, and auxiliary guest data, which of course was discussed. Such things like the IOMMU data and other driver data can be preserved. Other possible use cases, preserving database block caches, and I'm sure there's others. Limitations. Now these are, there's some limitations, especially concerning Bosch's work. One of them is that the preserving and restoring does add, or can add, a negligible amount of overhead. You got to walk those pages and store PFN, things like that, as opposed to persistent or emulate persistent memory where everything's just where you need it to be. Optimizations can help there. That's something I did in the patches as well. It's proof of concept. This, of course, does not work for firmware reboots. this is only for kexec of one kernel to another. And as Pasha mentioned, there's possibility of failure if you get overly fragmented memory from preserving bits and pieces all over the place. I do believe there's implementation solutions to this. Either by constraining allocations to certain areas or defragmenting, things like that. Another is that, of course, the kernel you're booting to has to know about but with the data it's getting from PKRAM and how do you get data from PKRAM. Another is that certain things can't be preserved yet. It's like huge TLB pages, for example. And I'm sure there's others, but those are the primary ones. Current state of the patches. I sent out RFC v2 a while back. It's got an API and supporting functionality. For example, it works with kernel or address space layout randomization. The randomization still works. It just has to be taught to not stomp on anything that's preserved. I implemented there's an implementation of a simple method for preserving TempFS files with PKRAM. Somewhat incomplete, but it's a good proof of concept. And a number of optimizations to show that speeds, performance is not necessarily going to be an issue. Parallelizing the work, deferring initialization of page structs for preserved pages, things like that. And finally, here we are. Questions or comments? I just briefly went over everything, but if you want me to get more details, I can.
So Anthony, you mentioned that one of the solutions was to preserve the memory that is going to be used for PKRAM in order to avoid fragmentation issue. But if that memory is preserved, we could just as well use PMAM in PKRAM, and then the reboot firmware would be supported.
Yeah, that's true. I was just thinking off the top of my head, I think there's other potentials like limiting how many pages can be preserved, perhaps, percentage of overall memory, or I'm just throwing out things. Or if you find it's really fragmented, to defrag it.
Well, defrag does not really work because we cannot move those pages that are preserved as page data.
Okay.
Right? It's just.
Not necessarily. Yes, some should not be moved. Like, if you're preserving IOMMU, certain types of IOMMU data. Others, though, like a regular TempFS file, it can't, you can move them. In fact, there's functionality, to avoid being clobbered or by kexec or having kexec clobber preserved pages. There is functionality to get preserved pages out of the way of where kexec intends to locate its kexec segments. And when preserved pages are found in that area, they can be we just allocate a page that's outside of the area and copy it over. For a regular file page, that's not a problem. In fact, if there's a huge page and it's in a bad area, we just break it up and relocate it to base size pages. It works, for data that doesn't have any dependency on its location. so I would say that's actually a limitation right now with PKRAM, is that certain data, there's a potential you could be relocated when you don't want to be. So yeah, so what I'm looking for is, I mean, it sounds like there's some interest for sure, is where to go with this next. You know, the APIs, an API of some type seems useful here. You know, are there elements of this implementation that just aren't going to do it, or the APIs, or in, you know, can this be morphed into something usable?
Well, in my opinion, if the interface is good in terms of you have this start saving data, then you select it's a stream of bytes, so actual pages that are not movable. But if PKRAM could be extended to survive across the firmware reboot, it would be much more appealing.
I see. So of course that would mean involving the firmware, but sure, you can definitely look at that.
Well, I mean, the firmware does not have to be modified today, but the point is that there should be a way for firmware to preserve the PKRAM data. And the interface we have today to work with firmware is the PMAM. So eventually the PKRAM should be able to use the PMAM.
Okay.
So for the Zen version, we actually ended up moving away from a command line parameter pointing the new kernel at, you know, the stored memory, and we put that in. We have patches upstream for kexec and a different type of kexec which passes that root pointer, we called it the breadcrumb, from one kernel to the next through kexec, which made it a little more versatile because you could have things that were changed after that kexec set things up. Because there's a difference between the kexec loading the kernel and setting the command line and setting up all its regions, and then the final kexec. So something might have changed. So we ended up with a completely in-kernel handover for that, which we could hopefully use from Linux as well.
Okay, yeah, that sounds interesting.
And if we're going to use this kind of mechanism for passing driver state from one kernel to the next, it really is going to have to be in kernel, some of it, you know, updated at the last minute rather than things that can be passed over because they were put there by user space. Yeah.
Okay. Okay. Yeah. You know, one of the advantages, at least with the command line, I'm to assume passing it through kexec can do the same thing, is that the compressed kernel, you know, obviously has access to the command line as well, or and can do what it needs to do to support KSLR and things like that.
Yeah, well, we had the opposite problem that we had to pass it through. I think we ended up putting it in a register somewhere, and then it had to be passed through. But it meant we could do more. We started off with it in the command line for Zen, and ended up moving it to the kexec handover. So we can possibly manage to reuse that same thing, because kexec is basically the same. You can kexec from Zen to Linux and vice versa. We did hypothesize about doing really stupid things like kexec from Zen to Linux and then have Linux resume the Zen guests, given that we can now run Zen guests on Linux. But we haven't got there yet.
Okay. So there's interest in RFC version 3, I take it. I think I'm going to probably have to, put things out in smaller pieces. Leave out maybe the proof of concept type code. So it does add up to a lot of patches.
I'd love to see made generic so that the TemperFest is just one thing that can be passed across the generic mechanism.
Mm-hmm.
And that lets us then expand it to do, individual device drivers can do support for passing their state over.
Mm-hmm. Okay, yeah, thank you for that.
You want a trivial device driver to start with, just pass over the loops per jiffy, right? That's one thing that the new kernel takes a long time doing if it's not passed over explicitly, and it's utterly pointless if the old kernel could have told it.
Okay, that's a good idea. Any other comments or questions? If not, I guess thank you. We can have 15 minutes back of your time.
Thank you, Anthony.
Thank you.
Thanks.
So we'll be back in 15 minutes for the NUMAware spin-off talk.
All right, it's about time to start the next topic. I'm going to put up Alex's slides, and maybe Alex, we could do a quick audio test right before you get started. Okay, I can see you on video, but I'm not getting any audio. Not hearing anything, no. Still nothing. Alex is trying to rejoin.
Can you hear me now?
Yes, I can hear you very clearly now.
Perfect.
All right, so I'll make you presenter again, and I got your video and heard your audio, so you're free to start whenever you'd like.
All right. Thanks, Daniel. So hello, everyone. I'm Alex, and I'm happy to participate in this micro conference and have the opportunity to talk about our work on NumAware logs and the corresponding patch set on adding NUMA awareness to QSpin log. Oh, sorry, I forgot to mention that this is a joint work with my colleague Dave Dice from Oracle Labs. And unfortunately, I think Dave couldn't be here today. So I would like to start with a very brief introduction to the topic of logs and NUMA, although I assume that most of the audience here are familiar with the topic. But just to make sure everyone are on the same page, I'll go very quickly over those slides. So logs protect access to the shared data and remain the most popular synchronization technique, perhaps despite the rise of other alternatives such as non-blocking synchronization. And even though people know how to implement logs for, I guess, more than 50 years at this point, they still remain the topic of extensive research. And the main reason for this attention is because it's well known that the performance of parallel software and the Linux kernel included often depends on the efficiency of the logs it employs. So logs come in many flavors. We have exclusive logs that allow only one thread in the critical section at any given time. Or we have reader-writer logs that allow multiple readers to be in the critical section at the same time, but only one writer can acquire the log for write at the same time. And then we have spinning and blocking logs, and logs that differ in the levels of fairness guarantees that they provide. The focus of this talk is going to be on exclusive fair spinning log, also known as the QSpin log in the kernel. So the last thing I want to mention in this brief introduction to logs is that logs evolve with the evolution of computer architectures, and we live in the era of multi-socket architectures with so-called NUMA effects. And so if you have software running on such a system, if you want to take advantage of those NUMA effects, we need NumAware logs. So what is NUMA? Well, in modern multi-node systems, access by a core to local memory or local cache located on the same node is faster than accesses to remote memory or remote cache located on a different node. And this is known as non-uniform memory access effect, or NUMA in short. And note that even if a system has a single socket, it may behave like NUMA on a die, where accessing certain memory or cache is faster than the other. But if your system has multiple sockets, it's pretty much guaranteed to have those NUMA effects. So how do log designers explore the effect to construct better numerable logs? Well, the general idea is to keep the log ownership within the same node. That is, when a thread wants to release the log, we want to make sure that the next log holder will be running on the same NUMA node. And by doing that, we decrease the number of remote cache misses and inter-node communication. So note that this happens not only on the log state, but also on the data access in the critical sections, since threads competing over the same log tend to access the same data or closely located one in their critical sections. At the same time, it's pretty clear that by keeping the log within the same node, we cannot guarantee strict FIFO. And by strict FIFO, I mean, strict fairness. And by that, I mean FIFO. And in general, those numerable logs tend not to be fair over short periods of time. However, most of those numerable logs usually preserve fairness over longer term, switching periodically between NUMA nodes. So all in all, numerable logs tend to trade off short-term fairness for better performance. Now, before I describe how our patch set modifies a QSpin log to bring NUMA awareness to it, let me spend a minute to talk about QSpin log itself. So spin log in the kernel is one of the most basic types of logs. It's ubiquitous and present in many internal data structures, such as file inodes and page structures. And as such, it has to be very compact, as any increase in the size of the log structure would immediately increase the memory footprint of the entire kernel. And it also has to be fair, although I have this question mark next to the question whether it needs to be FIFO, and we'll get into fairness discussion hopefully later in the slides. And it obviously needs to perform well under all levels of contention. So those are some of the requirements for spin logs in the kernel. And now let's see how spin logs achieve that. So on the first kernel, spin logs, the spin log was implemented as a test and set log, which is the simplest kind of log you can imagine. It is very compact and fast, especially for the no contention case, but it is not fair. And in fact, may cause starvation for threads trying to acquire this log. So later on, this log has been replaced with the so-called ticket log, which is also compact. It's fair. In fact, it provides FIFO, but doesn't perform well under high contention. And finally, about 8 or 9 years ago, the ticket log has been replaced by a queue-based log, hence the name QSpin log. And to be more precise, QSpin log today is a combination of a test and set log for the fast pass, for the no contended pass, and the so-called MCS log for the slow contended pass. So MCS stands for the Merrill-Crummy and Scott, who are the two authors who invented this algorithm, and it's a very popular user space queue-based spinning log. So the resulting QSpin log in the kernel is fair and performs well under low and high contention, at least when those NUMA effects I described before are not present. And when they are present, this log doesn't perform well, simply because it's not NUMA aware. So one of the main reasons I think that numerous NUMA aware logs from user space haven't made their way into the kernel so far is because those logs are typically built of a hierarchy of NUMA oblivious logs. And as such, they tend to use space proportional to the number of nodes. And this translates into hundreds of bytes of memory on a typical multi-node system. And it goes far beyond anything that would be considered reasonable in the kernel. So a couple of years ago, at this point, we came up with this idea called CNA, that stands simply for Compact Numerical Lock. So CNA requires just 4 bytes of memory, pretty much like the existing QSpin lock, or just one word when implemented in user space. It's a variant of the NUM-oblivious MCS lock that I mentioned before, and it has several advantages in this regard. So first of all, it inherits its performance features of MCS, such as local spinning and just one atomic operation per acquisition, and also requires relatively minor contained changes to existing MCS implementations, including the one in the kernel for the QSpin lock. Now, performance-wise, and I'll talk about performance more extensively later, but on a high-level summary, it performs on par with MCS under no contention, and on par with state-of-the-art hierarchical numerical locks when contended. Now, this latter part we, of course, could evaluate only in the user space, since those hierarchical numerical locks, as I mentioned before, are pretty large. But in general, when we compare the existing kernel with the one that has our patches, we can measure up to 3x throughput increase on a highly contended 4-node system. So how does CNA do that, or what's the trick? I guess on a very high level, so queue-based spin locks, such as MCS, organize waiting threads into, well, a queue. So the thread at the top of the queue right here will have the lock, and all other threads will join the queue and spin on a certain field in their queue structure and wait until the lock becomes available to them. Now, CNA uses 2 queues instead. So it has the primary queue for threads running on the same node as the lock holder, and the secondary queue for everyone else. So in this example, if colors represent the NUMA nodes on which threads are running, we'll have blue nodes on blue threads on one NUMA node and red threads on a different NUMA node, and we want to keep log passing the log between those blue threads. Now, how we do that? So MCS log holder checks whether the next waiter in the primary queue is running on the same NUMA node, and if not, it detaches that waiter from the primary queue and moves it to the tail of the secondary one. So schematically, that would look like that. So if we have, in this example, the blue thread number 1 holding the lock, when it wants to pass the lock to its successor, it will check and find that its successor in the main queue is a red thread. So it runs on a different node. It will move it to the tail of the secondary queue and pass the lock to its successor on the main queue, right? So we'll keep the lock as desired. We'll pass it to another thread running on the same NUMA node. So of course, if we keep doing that, just to add, so we gradually filter the primary queue, leaving only waiters running on the same preferred NUMA node in the primary queue and moving everyone else to the secondary one. Now, of course, if we keep doing that all the time, we will have the issue of starvation. And at this point, you can ask, well, what happens with the fairness or FIFO? So the high-level idea to ensure long-term fairness, we want to flush the secondary queue back into the primary one after a certain period of time or a certain number of intranode handovers. And there are several ways to achieve that, and we went through a number of options. And based on the feedback we have received on our patch series, we settled on the following. So we will keep track of the time since the secondary queue has been created, when the first thread has been moved into it, and after a certain time has passed since that moment, we will flush the secondary queue back to the primary one. And of course, there is the question, how much time? So it's a tunable parameter, and the default value is 1 millisecond, but it can be tweaked on the fly, so it doesn't require to restart the system if you want to modify that. Now, in general, CNA,
just a quick note for that. Users are going to get that entirely wrong. every time. In my mind, it's always better to leave these kind of decisions one for all users. Just do it underneath and don't let the user even be aware of that.
Okay, thanks. Thanks for this comment. So in general, though, this parameter, either visible or not to the users, it controls the trade-off between FIFO or short-term fairness for better performance, much like any numeral log has. So one thing to mention here, again, based on the feedback, we added this notion of prioritized threads who are excluded from this scheme. So for example, if a thread attempts to acquire the spin lock with IRQs disabled, it will be prioritized in the sense that it will stay in the primary queue and will not be moved to the secondary one, no matter the NUMA node on which it is running. So, now let me talk about some performance results. We have integrated CNA into the slow path of QSpin lock. We also evaluated CNA extensively in the user space as well, comparing it to MCS and some state-of-the-art hierarchical numeral locks. So I'll talk about results from a 4-socket x86 base system with 18 hyper-threaded cores per socket. So here is, in this chart, we compare the throughput of one of the benchmarks in the Willits scale suite of benchmarks for the kernel. And this benchmark creates contention on the spin locks in the kernel. And we can see that once we increase the load beyond 16 threads, the throughput of the original kernel drops, while CNA manages to keep the throughput stable and maintain the gap of more than 2x in this case. And up to 16 threads, when the contention is not significant, CNA and stock perform pretty much the same. Now, interestingly, CNA can help accelerate user space applications that happen to have contended pthread locks. And it achieves that by increasing throughput over the Futex chains underlying those locks. So in this example, the throughput of this well-known key value store level DB improves by almost twice when we apply the CNA page to the kernel and no change to the application itself. So we have a few other results in the page set description itself, and also on the mailing list, some of them posted by the kernel test robot. So here are a few examples of those results. And in a quick technical summary to CNA, so by achieving the efficiency of MCS at low contention and performance of state-of-the-art numeral locks at high contention, I think CNA is attractive and compact alternative for any NUMA oblivious lock, and in particular to MCS. And our page that introduces CNA into the slow path of the QSpin lock is available at this link here. And I want to spend a few minutes to talk about this page series in more details. So it has already undergone 15 rounds of review so far. And here's my opportunity to say a big thank you to everyone who provided feedback and the evaluation, especially Wayman and Peter, if they're here, who reviewed this page series extensively. But also thanks to everyone else who has chimed in. And of course, more feedback and evaluation results are welcome. I think the main hurdle that remains is this hovering question on whether we really need this. Or if I only slightly paraphrase one of the comments, shouldn't we be spending our time breaking those contended locks instead? And this is a fair point. And my answer to this is that we should probably break those contended locks regardless, since if we can rewrite our software to avoid lock contention in the first place, we should do so. But at the same time, more efficient locks help us to buy time for such a rewrite, especially when such a rewrite is a tough option, such as the case of legacy software. And even then, some locks might be inherently contended, such as when everyone wants to update the same file at the same time, and so the log protecting that file would be hard. And in the meantime, as our results show, if we keep ignoring NUMA, we leave essentially up to 3x performance on the table. Yeah, sorry, that is
I have a question. Yeah, so I think this helps to improve the average throughput, but I'm a little bit concerned about the worst case latency that this might cause, because I think you put the tunable as 1 millisecond. If we have a 4-socket system, say the worst case might be I have to wait for 3 milliseconds before I could actually acquire the log. So I was just wondering, like, if you have maybe done some workload that look at the latency aspect. Yeah.
So you're certainly right that that's the trade-off. One thing to point out is that when you have contended lock, you will be waiting for that lock in the queue no matter what, right? So with this patch, you might wait longer, just because you might have contention coming in from one NUMA node, and threads running on a different NUMA node will have to wait a bit longer. But yeah, I guess we haven't looked specifically into the worst case performance, but it certainly can can increase, in the sense that your waiting time can increase. Yeah, that's a fair point.
Hi, I would like to add that for RT real-time tasks, they are treated as prioritized so that they won't get queued into a secondary queue. So we will keep all the real-time tasks in the primary queue. So for processes that are latency sensitive, I suppose they should be running with real-time priority. In that case, it won't get affected by this.
Yeah. Yeah, and the other
thing, and similarly, preempt RT is going to have to disable this because of Ross Spinock, I mentioned it yesterday, went determinism, and they want that first in, first out semantics.
In addition, there's a class of real-time applications that uses no hertz full. And they're going to be spinning potentially at normal priority, not real-time priority, but the only thing on that CPU. But you'd want them to have privileged access to the lock nonetheless. Maybe you just say, go ahead and make them run RT even though they don't need to, but there might be some side effects of that. So another use case, a real-time use case to consider, the case where you have a CPU-bound real-time thread running on a single CPU is the only thing there.
So is there any way to identify those threads or tasks?
Yeah, there's some in-kernel primitives that you're going to hand a CPU to that'll tell you whether the CPU is in that state.
Oh yeah.
If you know the CPU.
Yeah, thanks, Paul, for this comment. I think it shouldn't be.
If you send me an email query, I'll get the actual thing to you. Or there's people on the call that probably know them off the top of the head, but I'm not one of them.
Okay, sounds good. We can certainly add them to this priority list, especially if the query is lightweight and wouldn't have any impact on performance. And in general, I think for everyone who asked those questions about worst case latency, if you have any suggestion for benchmarks who care about worst case latency, it will be I'll be happy to do more performance analysis and analyze the sensitivity of those benchmarks to this tuning parameter.
Yes, I'm concerned about one thing. So the linked list, the primary linked list that you have to go through and modify, that has a combination of things from different NUMA nodes. So you end up requiring remote NUMA node accesses at some point to go through that primary list, right? So, what I'm concerned about, or what I don't see is, why is this a requirement for the space that the lock takes? Why is it a problem to multiply that space by the number of NUMA nodes in the system?
I'm not sure I understand the question. So you're asking why we don't just inflate the lock and use one of the hierarchical locks instead, or?
Yes.
Well, so this so we don't change the Q-spin lock structure, right? So the existing Q-spin lock has only 4 bytes, and we use essentially the same 4 bytes for managing the lock. Those hierarchical locks are typically, you know, they need hundreds of bytes of memory just because you want to pad those structures to avoid fault sharing on the access to you know, to those locks that or to those threads running on different NUMA nodes. And I doubt you can put.
Oh, so that becomes a memory layout problem, which can be solved in other ways, where you could basically put all those locks into a per NUMA node memory area, and then use offsets to. We do that for PerseView data at the moment in the kernel.
Yeah, I mean, I guess it might be there might be a way to do that. It will probably introduce more changes to the existing Q-spin lock, but yeah, Tony.
Because then the advantage you get is, as long as you are within so as long as you're local within the NUMA node, nobody need to touch any NUMA memory from remote NUMA nodes until that ticket, let's say, gets moved to another NUMA node that controls the lock, and then everything becomes local to that NUMA node, and then somebody else gets another NUMA node gets a lock. So you basically batch the accesses by NUMA node. And get everything local within a NUMA node by using a hierarchical memory layout.
Yeah, so the thing to note here is that you do touch the structure of a remote thread, but only once when you move it to the secondary queue, right? And that's why you need this you know, period of time, 1 millisecond in our case, to reap the benefits of doing this reorganization, right? So that your next accesses to the successors in the main queue will be all local.
Okay, so what you're saying is accesses to remote NUMA memory is really rare. So it's only, let's say, each millisecond you get to touch other remote NUMA lines.
Yeah, exactly. So once we move this red thread to the secondary queue, right, it won't appear in the main queue until we flush the secondary queue back into the main queue, right? And so we will transfer the lock, we'll filter the primary queue, and we leave essentially only waiters on the same NUMA node. So during this filtering, we might we might touch those remote structures, but it's done only once, and you know, in aggregation, that's a very small overhead.
Yeah, but I'm thinking about use cases where you have short-lived locks. You have a primary queue filled with entries from various NUMA nodes, and then you end up, each time you need to take the lock, you need to move away lock entries that belong to different NUMA nodes than yours. So you end up always doing remote NUMA nodes access. So it has a worst-case scenario that's relatively bad.
Well, it will be as bad as the current Q-spin lock.
Yes, but I think you could do better if you go for a distributed locking hierarchy.
Well, I guess. I mean, that's a fair point, but I need to think more if you really can, implement this hierarchical lock in a way that you wouldn't have to access remote structures and be compact enough to be integrated in the kernel.
Yeah, thanks.
So one thing I think that would add more value to maybe starting to get this upstream or whatnot would be, I know you have a key store benchmark that uses Futex, I believe. Other than that, I'm just seeing micro benchmarks, which really aren't that interesting, considering if you want to add the complexity you want to add into this, like you really need solid numbers. And I think people would be more drawn to higher benchmarks, even benchmarking your own database, Oracle. Like if you provide results with that, basically just run more higher level workloads on it would be interesting.
Okay. Yeah. I mean, just like I said before, if there are any concrete suggestions for workloads with contained locks, I'll be happy to give them a try. Yeah, but certainly more benchmarks will help.
Yeah, it doesn't need to be a workload that only pounds on a lock. It can just be a generic high-level workload. Since spin locks are everywhere, like it's bound to, even if it doesn't show any difference, like it would still be interesting to see what shows.
Okay. Yeah, so some of those benchmarks, I mean, I do agree they're pretty small, but some of those, especially in this mailing list, I think they would be counted as more significant. I think those AEM 7 and FS Mark are more interesting than what probably you can find now page description.
Have you tried TPCC? Because I think for our TPCC teams, when I look at their profile, they have quite a bit of spin lock contention there.
Mm-hmm. No, we haven't. Thanks for the suggestion. All right, so this is my last slide with a bunch of links to resources, including paper that we published at URCs a couple of years ago, and a free copy is available on archive as well, and some of the links to things that I mentioned during my talk. And again, thanks for the feedback, and if you have more, feel free to reach me at my email.
Thank you, Alex. Yeah, that brings the end to the track. I'd like to thank everybody for coming, participating, and thank you again to our sponsors, and have a good rest of your day.
Thank you, everyone.